In section 731, we looked at the sampling distribution of a sample mean, and we were assuming in that part, the first part of the 7.3, we were assuming the population distribution was normal. It was known to us, and we knew it was normal. Here, we're going to look at what happens when the population distribution is not normal, or we just don't know what it is, because that's what's really going to happen most of the time, is we may not even know what kind of distribution, what kind of shape the population distribution has. And so what effects will that have on the sampling distribution of X bar? We know from 7.3.1 that if the population distribution is normal, the sampling distribution of X bar is going to be normal. So what we want to look at is what happens when it's not. Okay, so the first thing we're going to look at is we're going to reuse that web-based applet from that Rice University professor, and we're going to look at the first time we used this, the distribution. Population distribution up here was normal, right? And then we saw that we had population sampling distributions that were also normal if the population's normal. Now what we're going to investigate is non-normal population distributions, or in reality, sometimes we won't even know what the shape is. And so what were the results of that? So click on the begin button over here, and that will take you to the that begin button is in your electronic version of your PDF that's up on Google Classroom. So click on that on your PDF, and that should take you to this web-based applet. All right, so we want to talk about here the central limit theorem. And it's kind of an important theorem in statistics. And it's important because often we're not going to know what the population distribution shape is. We're not going to know that it's normal, or we know it's not normal, right? So either we know it's not normal, or we just don't know what it is. We need to use the central limit theorem to so that we can assume normality of our sampling distribution. All right, so it's pretty remarkable when you looked at that web-based applet that as the sample size increases, we noticed that the distribution of all the samples, which is sample means, which was the sampling distribution, is more and more normally distributed. And it doesn't really matter what shape the population distribution is, so long as our sample size is large enough, we can assume a normal sampling distribution. And so really the whole thing, that's essentially what the central limit theorem says, that if n is large, then the sampling distribution of our sample mean, x bar, is approximately normal. So like, okay, so how big is large? If we look at, this was sort of looks like one of the examples that we did. In case you didn't get a chance to open up the applet, let's kind of look at an example here. So here, if we did an approximate sampling distribution of size 2, you can see it's definitely not normal. A sampling distribution of samples of size 5, starting to look a little bit more normal. Sampling distributions from samples of size 10, starting to look even more normal. And then finally, a 1 of 25 looks pretty darn normal. All right, so we notice that as they get bigger and bigger, the sample sizes get bigger and bigger, that the sampling distribution of X bar will be approximately normal. All right, even if the population is horribly not normal, right? Strongly skewed to the right, or just some wacky distribution that is not even close to being normal. And so the central limit theorem is going to allow us to say that our sampling distribution of X bar is approximately normal. All right, so in order to do the probability calculations that we're going to want to do based on a normal curve, normal density curve, we're going to have to assume that our sampling distribution of X bar is normal. And there's two ways that we can do this. And so we're kind of taking everything that we've learned in these two parts of sections 7.3 and putting it together. So it all boils down to this. There's two ways in which we can assume a normal sampling distribution of X bar. And one is if the population is normal. So if the population distribution is normal, then it doesn't matter what the sample size is. We know the sampling distribution of X bar will also be normal. Okay, so that's one way. In which case we can just ignore the sample size. We don't care whether it's big or small. If the population distribution is normal, the sampling distribution of X bar is normal. And then if we don't know what the population distribution shape is, or we know it's not normal, so then we need to use the second method. We need to use the central limit theorem. So if the population distribution is not normal or just is unknown to us, then the central limit theorem tells us that the sampling distribution of X bar will be normal if our sample size is 30, at least 30 or more. All right, and so this will allow us to use normal probability calculations, using your z-score or your normal CDF, your inverse norm. All these things are now open to us for calculating probabilities that we would have gotten the sample that we did. How likely are we to get a sample or one more extreme than the one we did? And so we need to know that our sampling distribution is normal. All right, so let's look at an example. And we're going to use our 3 steps here. Suppose that the number of texts sent during a typical day by students at a particular high school follows a right skewed distribution with a mean of 45 and a standard deviation of 35. So remember too that our calculations for the mean and standard deviation of our sampling distribution are dependent on the mean, which is 45, and the standard deviation, which is 35, of our population distribution. And now those formulas work regardless of whether or not our population distribution is normal or not. So here we know it's right skewed, so we know it's not normal. All right, here's the question that we're trying to answer. How likely is it that a random sample of 50 students will have sent more than 2,500 texts in the last day? All right, so that sounds like we're asking number, as though this is some kind of binomial situation. But think about what we're asking. We're asking 2,500 texts by these 50 students. So think of it as a mean. We want to think of it as the probability that X bar is greater than or equal to that 2,500 divided by 50, or that the probability that X bar is greater than 50. All right, and so that's the first thing we want to do is write out what's the probability that we're looking for. We want to find the probability that X bar in our, how likely is a sample to give us an X bar greater than 50. All right, then we want to calculate what is the mean of our sampling distribution. And we know the mean is equal to the mu of the population distribution. Again, it doesn't matter that the population distribution is not normal. So that's because the X bar is an unbiased estimator. So remember, the sampling distribution of X bar will have the same mean as the population mean. All right, then we want to calculate the standard deviation, but before we do that, we have to check our 10% rule. So we have to assume that there are more than 500 students at this school, that we are not sampling more than 10%. All right, after we've checked such a thing, now we don't know. We just have to, they didn't tell us that there's more than 500, but we just have to make that statement. There would have to be more than 500, and then that covers our butts. All right, the next thing then is, since we are taking care of the 10% condition, we now calculate the standard deviation of the sampling distribution of X bar. That's the population standard deviation divided by the square root of 50, the sample size. All right, then we have to we have to state how we know that the sampling distribution of X bar is approximately normal. All right, we're told that the population distribution is not normal, but our sample size is greater than 30. So the central limit theorem tells us that our sampling distribution of the X bar is approximately normal. And then the last sixth thing is write out what that distribution is. So it's normal with a mean of 45 and a standard deviation of 4.95. All right, so now let's look at how we would do our calculations. Two parts to that. First thing you want to do is do a shaded curve, right? A normal curve with labeling and shading. All right, so it looks like our mean is 45. We want to be greater than 50, so we shade at 50 and to the right. And now use your calculators. I mean, you can certainly use your z-score and your z-score tables, but your normal CDF would probably be a better choice here. It seems like it's always faster. And so we get about 15.6%. And then we want to finally answer the question in the form of a sentence. All right, there is about a 16%, or if you said 15.6, that's fine too, probability that a random sample of 50 students will have sent over 2,500 texts in the last day. All right, so again, 9 steps here. We want step 1 involves 6 components, and then step 2 involves 2 components, and step 3 is the 9th component. So, again, on any kind of assessment or test where you're asked to do a 3-step, it's worth 9 points. So silly to lose any of those points. All the multiple choice on the assessment are generally equal to 1 open-ended question. So, the multiple choice are a little tricky, but they're pretty straightforward. You just have to learn the format, make sure you're including all 9 components so that you're not losing any points. Make sure that you're doing that on the homework as well so that you're practicing all the components that you need. All right, so let's get a visual. You don't have any more of these slides. We're going through a couple more slides here, but you don't have any of these in your notes. This one is just kind of a visual of what's going on here. So we have some kind of population data. Maybe it's the arm length of high school seniors, and normally distributed. Maybe it's not normally distributed, but in this case, it's normally distributed. We take and we sample. In theory, we would sample every possible sample of the same size. We would take each of those samples, calculate the X bar, and plot them in the sampling distribution. So again, the sampling distribution of X bar would be the distribution of all possible sample means from all possible samples of the same size taken from that population. So often when we do graphs, we're doing, and the web-based applet was creating an approximate sampling distribution, say with a 500,000 samples, not every possible sample. Sometimes there would be times 10 to the 23 or 27 number of samples. Usually we do not create an actual sampling distribution. It's a theoretical. If we were able to take all of the samples, all the possible samples, right, of the same size, plot them all, it would give us our sampling distribution of X bar. All right, let's review a little here. for chapter 7 for our assessment. So for each distribution below, identify each underlying number as a parameter or a statistic, and then use the appropriate symbol, like p hat equals blah, blah, blah. All right, so the first one, nationwide, 84% of people are living in the same house they were living in 1 year ago. The Town Council of Pleasant Valley surveys 100 residents and finds that 75% of them have not moved in the last year. Okay, so we have two numbers. Which one's the parameter? Which one is a statistic? What symbols would you put in front of those? Well, the only statistics that we're dealing with are, for the most part, are sample means and sample proportions. So think about whether those are sample means or sample proportions. All right, and so the 84%, that is dealing with population data, right? Because it's nationwide, whereas the 75% came from a sample, and so that's the statistic. All right, so P, the population proportion, is 84, and the sample proportion is 75%. All right, next one. The mean birth weight of infants in the United States in 2006 was 3.3 kilograms with a standard deviation of 0.57 kilograms. An obstetrician determines that among her own patients, the mean birth weight was 3.6 kilograms. All right, now in this case, there's three different numbers underlined, so you have to come up with three different, say whether those three are either parameters or statistics, and then what symbols go with those. All right, so the parameters, there's two of them. This 3.3 kilograms is the mean weight. That's that is mu. That is from a population, and then the 0.578 number, that is a standard deviation, but it is a population standard deviation, so we use sigma to denote that. And then the other one is from a sample. Maybe it's not really a random sample in this case, but it's a sample, and so we'll use an X bar for that. All right, this last question is dealing with variability and bias. So at the right are histograms of the values taken on by three sample statistics. This is all very theoretical here, in several hundred samples. So we're talking about sampling distributions of several statistics. The true value of the population parameter is marked on each histogram, so you can see down below. All right, so which statistic has the largest bias among the three? All right, so when we talk about bias, it's like which one is has a center that's off, right? And so that would be C. C is not, as the parameter is more marked here, but the center of the sampling statistic, the sampling distribution, is probably more right here. The other ones all seem to be right about in the middle, both the mean of the population, the parameter, and not the mean, but the statistic. So the statistic of the sampling distribution is centered right at about where the parameters is. So those are much less biased. So this first one has a much more bias. It is much further off. Okay. The next question then. Which statistic has the lowest variability? All right, so it looks like clearly A is the one that has the smallest spread, the smallest standard deviation, smallest range, if you will. So it has the lowest variability. All right, so based on the performance of the three statistics, in many samples, and based on the approximate sampling distributions of the statistics, which statistic does the best job at estimating its parameter. So I think we would all agree that C is the worst one for sure. A and B both seem to have approximate sampling distributions centered at the true parameter value. So that means A and B are both unbiased estimators, it appears. But which one then would be better? I think we all agree A is better because it has not only low bias, but low variability, and that's what you want. All right, so your homework is listed here. There are 2 3-step problems. So I'm not telling you which ones they are this time. You should be looking at those homeworks, trying to figure out which of the 2 are 3-step problems. It's kind of important so that when you take your AP test, they're not necessarily going to tell you, hey, you got to use 3 steps here. I typically tell you on my assessments, but they won't. So a little practice here at figuring out, should I be using a 3-step process to calculate my answers.